Hi viewers, welcome to LM Solution. Today we are going to see about PV battery powered BLDC motor drive with flying squirrel optimization MPPT. So this is a simulation model we developed for flying squirrel optimization MPPT for PV battery powered BLDC motor drive. So this system consists of PV panel, battery and then BLDC motor drive. So here you see that this is a PV panel. The PV panel having single series connected model, two parallel strings. The single array will be generate 49.9, that means 50 watts. The voltage is around 17 volt and current is 2.941 amps. So it can generate maximum power of 99.99 watts, that means 100 watts at the voltage of 17 volt. So it's going to be connected to the DC link. So this is a DC link, or this is the DC link via this boost converter. So this boost converter will be boost the voltage from 17 to 24 volt. So here we are using the DC link voltage is 24 volt. So this converter going to be convert that 17 to 24 by means of this boosting operation. And also this boost converter going to be controlled by means of flying squirrel gauge optimization MPPT. So next here we have battery. So battery is rated at 12 volt. Rated capacity we are having 100 Ah. SOC initial is 50%. It's going to be connected to the DC link via this bidirectional converter, and this bidirectional converter going to be controlled by means of voltage control method. That means we are going to measure the DC link voltage and going to be compare with the reference voltage. The reference voltage is 24 volt, and it's going to be processed after comparing that we are going to process via PA control, and it's going to be control this bidirectional converter. In DC link, we are connecting this BLDC motor drive. See, they having voltage source inverter, so it is act as an electronic commutator, and this is BLDC motor. We are measuring the Hall sensor. So here we are measuring Hall sensor, and it will going to be converted into back EMF. So it is having some logic. So this is the logic. So Hall sensor to back EMF logic. So for each Hall sensor output, right, it having some digital output 0 and 1. So for each Hall sensor output, we need to map with the back EMF calculation. So this is a calculation for back EMF. So this is a implementation diagram of that conversion of Hall sensor into back EMF. Just we are using AND operation, right? So that means here is the drive for calculating back EMF of EA, EB, EC. Just you have to comparing that Hall sensor A and complement of Hall sensor B, and we have to do AND operation. And also you take Hall sensor B and complement of Hall sensor C, and then take complement that means AND operation. And then here you take Hall sensor C and the complement of Hall sensor A, and then take AND operation. And then you take reverse. So here you take HE and complement HV. So here you take opposite operation. Okay. And then finally you have to subtract both plus minus. Then finally you will get the back EMF. So here next we are converting that back EMF into switching pulse. That means that BLDC drive is connected via voltage source inverter. It having six switch. So that 6 switch should be controlled based upon back EMF. So back EMF having 3 state 0, plus 1 and minus 1. So according with each state, right, we have to generate a switching pulse. So here you see that, right, we are comparing that back EMF with greater than 0, less than 0. If it is greater than 0, it will be generate the pulse for Q1. If it is less than 0, it will be generate the pulse for lower. That means this is a first arm upper switch. So first arm lower switch. Same way the back EMF B, right? Is P is compared with greater than 0, less than 0. So this is second arm upper and lower switch, this one. And back EMF C will be compared with greater than 0, less than 0. So this is a third arm upper and lower switch, okay, in the voltage source inverter. And finally this will be used to control this voltage source inverter to control that BLDC motor system. So next to move on to that concept flying squirrel gauge optimization for boost converter. So here we are measuring the PV quantity like voltage and current. So here you see that, right? So here we are measuring the voltage and current. So that going to be input for a flying squirrel gauge optimization MPPT. The output will be duty cycle, it will be compared with the 1. So here you will get 1 minus T and it will be multiplied with the DC voltage, then you will get a reference voltage. So this reference voltage is going to be compared with the actual PV voltage and going to be processed via PA controller, and it will be generated the duty cycle. This duty cycle will be processed via PWM generator. So it will be generated the pulse. So this pulse we used to control the boost converter of the PV panel. So when go inside, right, so this is a code for a flying squirrel search algorithm. So here you see that this is the parameter we used to for a flying squirrel search optimization. So here is the probability threshold, air density, velocity, surface area, drag coefficient, lift coefficient, height from the ground, surface friction, planing control gain. Okay, and then you have to calculate the drag force and the lift force and the glide angle, gliding distance, and then you have to calculate that personal first. Okay, exploit or explore the based on probability. So this is a exploitation stage. Okay, so you have to calculate that the duty cycle based upon that exploitation. So this is hickory tree gliding concept. Okay, and then here you can see that we have to find a global best. Okay, so this is equation for global best, and then it has some conditions. Okay, so based upon this condition you have to calculate that one, and then here we are going to apply levy flight concept also. Okay, so this is a code for a flying squirrel gauge optimization MPPT. So these steps used to generate the duty cycle. So this will be every sample, it will be a calculated duty cycle. So the duty cycle will be processed here. Okay, and finally we are generating the pulse according with that operation already explained to you. And final pulse, this pulse will be control this IGBT of the boost converter to extract the maximum power from the PV as well as boost the voltage from 17 volt to 24 volt. So next comes to bidirectional DC-DC converter. So already told, right, when we control by means of DC link voltage control method, you have to measure the DC link voltage. So here we are comparing the DC link voltage with the reference voltage and going to be processed a PA controller, and it is going to be processed via PWM generator. So output of PA controller nothing but the duty cycle. So then PWM generator is generate the pulse according with the duty cycle. So this duty cycle going to be control this 2 IGBT of the bidirectional converter to maintain the DC bus voltage at 24 volt. So here you can measure the PV voltage, current and power. So here in this point you can measure battery voltage and current, and here you can measure battery SOC. So here you can measure the PV converter current, battery converter current, load current, and here you can measure the power of the power measurement, right? Converter power, battery converter power, load power, and the load voltage. So here I'm going to change the irradiation from 1600, 400, and then again we are changing 600 every 1 second. Okay, so just I'm going to simulate the model, and then I'm going to open the graphs. So this is a PV voltage. The PV voltage is maintained around 17 volt. So this is a PV current maintained around 6 amps, and then PV power is around 100 watts. So this is a battery voltage and this is a battery current. So battery current is negative, that means it is in charging mode, because load power is around only 60 watts. So excess power will be used to charge the battery. So after 1 second irradiation changed to 600, and then PV power generating around 60. Here you see that red battery current comes to positive. So that means it going for a discharging mode, because the load power is comes around 60 to 70 watts, right? So we need to have some system events, some losses also. So that will be take care of battery. At the time of 2 seconds, right, PV power comes to 40 watts because the irradiation comes to 400 watts per meter square. So now the load needs some power, so that power taken from the battery. Excess, that means additional power requirement will be taken from the battery. So you will see that, right, battery keep on charging. And now here you see the total speed of the BLDC motor drive, and also this is the torque of the BLDC motor. So this is the stator current and the electromotive force of the BLDC motor. The system will be work effectively according with the change in irradiation condition. So due to change in irradiation condition, the battery comes to charging and discharging according with that power balance in the system. If it is excess power in the PV, then battery going for charging mode. If it is no excess power, that means that PV power is less than load power, then battery will be comes to discharge to supply the power requirement according with the load demand. So this is the working of that model. Thanks for watching our videos. Kindly subscribe channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.